Okay, good morning. Let's get started here. So today we will finish up discriminant analysis. We will start the next subsection, nearest neighbor classification. Reminder that project number 3 is due on Tuesday, November 21st at 5 p.m. We'll talk about that a little bit later today as well, some more. I do want to bring up one thing that I wanted to mention last time that I failed to, and that is the project itself is divided up into 3 different parts in terms of the 3 major topics that we're talking about right now. And one of the topics is called logistic regression. I'm not for sure how far we will be able to get into that before the due date of the project. So do note that I might reduce that part of the project, meaning remove some of the parts or problems for that part of the project, and remove it so that you don't have to do it. Okay. Right now, I am anticipating that at the very least, we will get through 1 through 3 before the project's due date in terms of you having a sufficient amount of time to do these problems on the project. We might not be able to get to 4 and 5. But the reason why I put all 5 problems there, even knowing that we might not get to all of them, I put that there because these are what I think are the most important topics for this particular section, so that when you're studying for the test, you realize, okay, even though if we don't do 4 and 5 for the project, this is still very important. I better know how to do that stuff for the test. Okay. So are there any questions before we begin? So with respect to discriminant analysis, we were looking at this place-kicking data set. And we saw that, overall linear discriminant analysis using an equal covariance matrix, but prior is proportional, was maybe a little bit better than all the rest in terms of the other methods. But here's something also to think about here. In this data set itself, we have only 163 failures. So 11.44% of the data is failures. The remaining 88.66% is successes. So how about we just classify all our observations as successes, and voila, we have a new way to determine what cake is a success, what cake is a failure, and this gives us the highest overall classification rate. That's it. That's a lot simpler than what we just did. Well, why don't we do that? Well, the overall classification rate isn't the only thing that is of interest. When we would like to understand too the proportion of observations that are successes that we classify correctly or predict correctly, and the same thing with the failures. And in other applications, this holds true as well in terms of, while often a lot of focus is on the overall correct rate, depending upon the application, you might want to really focus on some of those other measures as well. But one of the reasons why I like to bring this up when I teach this topic is that you may outside of this class, face a similar situation where you have such a, let's say, uneven distribution of your 2 groups, or 3 groups, or 4 groups, however many groups or populations you have. And because of that unevenness, something like this could happen. In an extreme situation, let's say I have 1,000 observations, and only 10 are, let's say, from group 2. 990 are from group 1. Well, in that situation, if you just simply classify everything as group 1, well, you have a 99% overall rate, but you're going to miss all those group 2s. And in most applications, you don't really want to miss them all. So please take that into account. Now, whenever you do a discriminant analysis or some of these other methods that we're going to be using to try to predict classifications, groups, you want to do some kind of summary plot so that you can better understand, what you're getting right and what you're getting wrong in these predictions. So in a simple situation, suppose that this is my data here. I have two groups, two populations. I also have just two variables, x1 and x2. The plotting point corresponds to the actual group of the observation. And just from looking at the scatter plot of the data, immediately you would think, okay, I'm going to have some successes in terms of being able to do prediction here. And once you see this plot, then you do your discriminant analysis methods, and then you can also produce a plot that looks like this. And this is what happens to discriminant analysis, and we'll talk about this more shortly. Basically, what discriminant analysis is doing is looking for the best dividing line. And we can see by the points that I have colored differently there, the ones that the method is getting incorrect and the ones that are actually being predicted correctly here. And depending upon the application, you might be able to somehow explain why these particular observations are predicted wrong, or it might motivate you to think about, well, what other information I could collect about my data so the next time I try to do this, I can get it right. At the very least, you can imagine that, let's say you write in a paper for a journal, and you present some results that, oh, hey, I am predicting 90% correct. That editor or the corresponding referees for your paper are going to probably ask you, where did you get it wrong? Tell me more about this 10%. Did you investigate that? These kinds of plots then help you do that. And so that's why it's always good to do plots like this. Now, of course, in most situations, you're not just going to have two variables or three variables. You could do exactly the same plot like this. So instead, then we go back to our previous experiences about how to plot multivariate data. You could do a parallel coordinates plot where, you have the color of the line corresponding to what was originally observed for the groups, then do another parallel coordinates plot and have the line color correspond to your prediction. You can see where you're maybe getting things wrong. There's other variations of that. For example, maybe observations that you're predicting wrong. To show that on a parallel coordinates plot, what you could do is make them dashed lines versus just solid lines so that you can see that better. For this particular case, though, what I decided to do for the place kicking data was let's do a parallel coordinates plot. Let's do principal component analysis, where now I'm going to have the plotting point corresponding to what the predicted groups are. And this corresponds to linear discriminant analysis, equal covariance matrices, proportional priors. So in other words, it's actually this right here. Okay? And so we can see what's happening here. The discriminant analysis method tends to predict those that have higher PC number 1 values as failures. And I don't know why I didn't do this, but I didn't put a legend on the plot. Black is failures, red is successes. And so we can see almost like a dividing line here, essentially. It's close about what's happening. Remember what PC number 1 corresponds to. One particular component that's very important is the distance of the place kick. The larger the PC number 1 value, the larger the distance of the place kick. So in order to explain what the method is doing, again, think of it from a point of view of writing a paper, you're going to say, well, discriminant analysis tends to predict the much more longer place kicks as failures. Now, why is it doing that? Well, then this is when you go back to one of our original plots where we did principal component analysis. Eventually, I'll get there. Let's try to do this a little bit faster. There we go. And so this is what we had originally. And we can see that towards the right-hand side of the plot, we tend to have more of the blacks than we have the reds. So this is why discriminant analysis is doing this. But we can also see, and we talked about this at that time, that, yeah, I have a feeling that discriminant analysis isn't going to get everything right. You know, we have too many overlaps of those points there. And that's what we actually found to occur. Okay? You could look at it in three dimensions as well. Okay. Let's see here. You could do a similar plot. I thought I had it in the notes, but I don't see it. Maybe I'm just missing it right now. You could also do a similar plot with the validation data as well. Okay. So here's a question for you, and this is more so dependent upon your past experiences before coming into this course. And that is, suppose we have, and notice what's in red there, it's something I added, an independent variable that we want to use for discriminant analysis. It has three levels, simply A, B, and C. How would you include this variable in a discriminant analysis? You know, this has categorical levels, but in order to do discriminant analysis, you know, we saw these matrices that we had to form, these vectors. We need to somehow make these numerical values. What would you do? If you've had a course like Stat 870, our regression analysis course, which is recommended for this course, this hopefully would be simple for you. Exactly, using dummy variables. So there are what are called dummy variables. I don't like the name because of the negative meaning to it. I usually call them indicator variables. And here's why. Suppose we have a situation instead where we just have two levels, A and B. Okay? How about we create a new variable, we'll call it x1, that is a 1 whenever you observe B, a 0 otherwise. Okay? It indicates, well, is it B or not? Notice here, I only needed one variable for a two-level independent variable that has these categorical levels. One variable, two levels overall. In our situation, we also have a C level. So how about if I just create another one that indicates its level C? And so the way that I would actually include now this independent variable in my discriminant analysis is that I could actually create two indicator variables for this three-level categorical or qualitative variable. That's how you do it. R will automatically do this for you, but it's good to know, well, what is R doing? Also, R will do it in this format here. So you might be wondering, well, why don't I just, use this format instead? You could do that, but the way that R is set up is it uses some terminology now that you might have heard in another course. It uses set the first level to 0 as a format for converting these qualitative categorical variables into a numerical format. If you by chance are familiar with SAS, SAS does this. SAS uses the set last level equal to 0 format. Okay. Because that is then assigning a numerical ordering that, if I did do this, and just create one variable, then you're saying C is greater than A. Depending upon the application, that may or may not be true. Most likely, at least my intent here was it wasn't true. No. is just meant to be as a way to say I have three categorical variables, three categorical levels, where I'm not saying necessarily one is more meaningful or one is more greater than another. So, for example, so I teach a course on categorical data analysis. One example that I use in that particular class is that there was actually a study that was done here at UNL to understand the post-eating exercise habits of students who went to the rec. And students who were given the choice between, let's say, a brownie, an apple, or neither. There wasn't meant to be, like one being better than the other. Now, you can kind of think, okay, an apple's better than a brownie in terms of nutrition and stuff like that. But is neither better than an apple? Is neither better than a brownie? And so in that particular case, there isn't necessarily a natural ordering.
Yeah, but even if you use 1, 2, 3, and you already set it to categorical, and 3 is not greater than 1.
Well, the question was, why couldn't we just, let's say, create one new variable, call it X, and have numbers 1, 2, 3 for it in our data analysis? What this will do is assume then that level C is greater than level B is greater than level A by using that numerical ordering. So, for example, we can think of it in terms of a regression model. Let's say I have some response variable Y. I'm interested in what would I expect Y to be on average. So the expected value of Y, and a way to represent your model would be like this. That would be one way. Another way would be like this. Okay. In this first way here, which corresponds to using this numerical format here, you're saying, for example, that, if I have, let's say, X being levels representing level C, I have expected value of Y is equal to beta 0 plus 3 times X. I'm sorry, 3 times beta 1. This is for level C. If I had level A, now my model is, and so you're saying there's a linear trend. And you're saying that level C is more than level A. Now, instead, if I were to, let me do some erasing. Instead, look what happens with using these indicator variables. So for level C, my model is for level B, my model is this. And then for level A, I'm running out of room. My level is this. And so you can see how it's uniquely identified in the model. And I'm not necessarily, beta 1 could be negative or it could be positive. Same with beta 2. And so that's why we use indicator variables. Okay. Any other questions? So, whenever you have a lot of variables that you're working with, you might be thinking, okay, well, if I don't need some of the variables, let's not include them in the analysis. If these variables are not important for me to predict, let's say, success or failure for a place kick, why should I even include it? Going into the analysis, you probably don't know, is it important or not? And you're basically going to collect information on as many variables as possible that you think possibly could be important. And so you might want to do then, during your analysis, something called variable selection, where you want to select which variables only that are important, include them in your analysis, and not have to worry about anything else. Now, that is a topic, again, with like Stat 870, you see talked about a lot. You want to find a regression model that is often referred to as the most parsimonious but yet best predicts your dependent variable. Parsimonious or parsimony means the model is as small as possible, smallest number of variables as possible, but yet still predicts the dependent variable very, very good. And so you might think of something like that here. It's been my experience that, at least for this kind of a topic, you don't see variable selection done very often. And the primary reason is that notice we're not really focusing on the interpretation of the variables. All we're really interested in is what is the correct overall classification rate or prediction rate? What is how good am I doing for, let's say, one level of my grouping variable in terms of predicting it, or how am I doing with respect to another variable, and so on. And so that's why you don't necessarily see variable selection done a whole lot. If you look at multivariate analysis books, rarely will you ever see that topic in there. There is one book that does do that, and that is Dallas Johnson's book, and this is on the syllabus as a reference. Just a little bit of a side note here. Dallas Johnson was actually a professor of mine at Kansas State. And as kind of a test version of his book, he actually tried it out on my class. And obviously then that was many, many years ago, and the book was never updated. However, it appears that it will be updated soon. Former, well, I guess a student who went to Kansas State with me at the same time, he's going to actually be involved with writing a second edition of it. So I really, really like this book. I just wish it was updated with what has happened since the late 1990s. Even though the 1990s were really, really good, things have evolved since then. Anyway, but just on Friday, he asked me if I would be willing to review his book. So stay tuned for that. And this variable selection, I almost took this section, it's one of those things, as you've heard me before, I almost took this part of the notes out, but I just couldn't. I think I kind of liken it to, and my wife could vouch for this, I don't like to throw certain things away. She'll say, well, you're not going to use that. I said, well, who knows? Maybe down the road I might again, And I think I do the same thing a little bit with my notes. It's an interesting topic. And Dallas Johnson has an interesting way to approach variable selection. He draws connections to something that will be taught in Stat 802 called analysis of covariance, which is, if you haven't seen that before, it's very similar to analysis of variance. The only difference is now you also have, in addition to categorical variables, which represent the treatment levels, you also have continuous variables as well, trying to predict the dependent variable. And so he uses analysis of covariance to try to do variable selection. The one problem, and he admits this, is that it never actually gets to the main question at hand here, and that is, if I remove this variable from being consideration, does it reduce how good I can predict the grouping variable? It doesn't do that exactly. I won't get into further details than that. It's an interesting approach. You're welcome to take a look at it, but you're not responsible for it. So then we come to about the end of the notes here. We have some just additional comments. This first one I've already talked about, and that is, while most of the notes are set up for looking at a case where you have two populations or two groups, what happens if you have three, what happens if you have four, and we simply have direct extensions to more than two groups. We might calculate a Malhanomis distance for, let's say, three different groups. and look at the distance that is the smallest, and that's what you would classify that observation into. Then you could also use this with the posterior probabilities. It's really simple. So, you just extend the definition of what, one of these posterior probabilities looks like. And just to emphasize how this would be done, we would do something like this for 3 groups, where now this posterior probability is exactly the same as before, but now we're taking into account also that third group in the denominator. And we will calculate these probabilities for all 3 groups. The group that has the highest posterior probability corresponds to what you would predict for that group, for that observations group. Now, the way that discriminant analysis is set up, this is the second comment now, is basically, and I alluded to this earlier, is looking for basically, in the end, the optimal dividing line between your observations to best classify or predict the groupings for your observations. And I've taught it a long time ago, but I don't do it anymore because this can only be easily done when you have just 2 variables. But you can actually figure out what that line is in discriminant analysis. And so if we did have 2 variables, you might have something like this where we have, let's say, 3 groups, the blue, the green, and the kind of looks like yellow. And basically what discriminant analysis is going to do is try to optimally place a line between all the groups. And so that, let's say, any new observations that fall right here will be classified as a blue group. Drawing lines like this, you can imagine 3 dimensions, 4 dimensions, 5 dimensions, essentially the same thing is going to happen. Drawing lines like this can work well in many situations. In other situations, it might not work as well. These have to be straight lines. And so here's one situation where this is, let's say, our observed data, and you can see that it's going to misclassify or mispredict some observations in this particular case. So you might be thinking, well, is there something that's more flexible than that? Yeah, there is. And we'll take a look at something in the next section that is more flexible. But with flexibility, though, that flexibility, though, might prevent it to work well in a situation of, let's say these blue ones were like right here. Well, I'm not going to do all the greens. But let's say if I have observations that are right up next to each other. That flexibility, because the observations are close, might cause some misclassifications, mispredictions, where a linear discriminant analysis will be able to still do it very, very well. So no method is always best. That's why there's multiple methods out there. And so lastly here, this gets to something I mentioned at the beginning of this, towards the beginning of the section, when we first talked about a holdout data. Let's say that you have a data set and you want to do an approximate, let's say, 80%, 20% split. 80% goes into training, 20% goes into your validation data set, and then apply your methods to the 2 different data sets. How can you split the data? There's multiple ways to do this. This is just an example of one. Okay. So first of all, I want to kind of emulate what would actually happen in practice, where let's say all the data was in one data frame. And so what I'm going to do is take with my place kicking data set here, I'm just going to put together the original training data set, which was called place kick, and then also the validation data set, which was called valid. And so the way that I can simply put everything together is I can use a function called rbind, which means combine by rows. So in other words, I'm going to take my place kicking data set, put it here, and then right below it, I'm going to put my validation data set. That's what the data, this new all.data is going to look like. The total number of observations then that I have is 1,707. Now that I have that, I like to be able to do an 80-20 split. Here's one way. I'm going to do it at random, and so that I can replicate my results here, I'm going to set a seed. And I can use a function called sample.int. Int stands for integer. And what I'm interested in sampling is all the numbers from 1 to the 1707. If I wanted to, I could have put 1 colon there and dot all for that 1707. But if I don't do that, this will be equivalent, given how this function works. And how many do I want to sample? So that's what the size argument is. And like I said, I want to do an 80-20 split. So I'm going to take n.all, multiply it by 0.8. Since that's not an integer itself, then I'm going to round. So I'm not going to get quite 80-20%, but it's going to be very close. And so I'm going to take a sample of 1,366 integers for the integers from 1 to 1707. I'm going to put that into an object called obs.num1 for the lack of a better name. Oops. And this represents which observations I'm going to pull out of my all.data and put into my training data set. So to do that then, all.data, bracket, obs.num1. This corresponds to then which row numbers to take out of that data frame. Let me make this a little bit bigger. I guess it's fine. And so I put that into place kick 1. Number of rows of place kick 1, notice 1366. Now how do I form then my validation data? This is how I did it. Notice if I say 1 colon n.all, I'm going to get all integers between 1 and 1707. Eventually we'll get there. And basically I want to say, you can say, well, this is a vector. And I can say, okay, I do not want those corresponding numbers corresponding to which observations I'm putting into my training data set. So that minus there means no, I don't want that. I put that into obs.num2. And now this corresponds to the observations that will be in my validation data set. There is no overlap between obs.num1 and obs.num2. So once again, I can then go back to all.data and just simply pull out all those observations, put them into what ends up being my validation data set. Here's another way that I could have done exactly the same thing that I thought of when I was going through my notes. I'm not sure why I didn't do this. I could have just done that and get exactly the same place kick 2. So. I guess there is one other small thing. There's another version of discrim analysis called canonical discrim analysis, which kind of combines some of the ideas of how I approach discrim analysis in terms of, remember how we, did a principal component analysis, and we use that to kind of visualize, what is discrim analysis doing for us. What canonical discrim analysis does, it says, okay, let's form new variables similar to principal components. Instead, they're called canonical variables. And we perform discrim analysis on those canonical variables. I used to teach that. In various revisions of this course, that was something that didn't make the cut. I did take that out, and I didn't leave that in the notes. So it's just another approach. I know an individual who also teaches this course will talk about that. I just don't do it anymore. Okay, any questions?
Is there any way to determine what percentage of your data are going to go to training, or it's just up to each individual to choose that?
It is up to every individual to choose that. You know, there isn't a standard out there for you should always do this, you know, an 80-20 split. You know, I mentioned the 80-20 split. That is usually the most extreme in terms of the difference between the training and the validation that I've seen. The other most extreme is a 50-50 split. It's dependent upon, let's say, the number of observations you have, because obviously, if you don't have that many observations and you still wanted to do the training validation, then you know a 20% for your validation might not be enough to really truly evaluate. And so you might more lean towards the 50-50. There's actually, I guess, justification for otherwise to do that too, because you might be thinking, well, if you're only doing 50-50, you might not have enough observations to do well with your training data as well. So that, you know, that's part of the reason why there isn't a set standard out there. But you know, typically what I've seen in the past, and I agree with it, 80-20 to 50-50. So, any other questions? Okay, so the next topic is nearest neighbor classification. I think in the project, for some reason, I called it nearest neighbor analysis. I guess since I was just wrote up the discriminant analysis section, that's why I called it that. It's not a big deal what exactly you call it. The main thing is you need to say nearest neighbor. There's a number of different ways to apply nearest neighbor. We'll talk about the most popular way that I see. It's also the way that's mostly introduced as well. And this method doesn't rely on any kind of multivariate normal distribution assumption like what we have with discriminant analysis. And because of that, this particular kind of method is referred to as a non-parametric method. In statistics, there are what are called parametric methods and non-parametric. Parametric means you have an underlying probability distribution that you use, like multivariate normal. Non-parametric means you don't. So this is one of the most flexible methods out there. You know, you're not going to see like a straight line on one of those plots that helps divide stuff out. And this method is actually very intuitive. You know, let's say you have a particular observation and you want to know, okay, should I classify this into group 1 or group 2? Suppose we just have 2 groups for now. And so you might be thinking, okay, how about we look at some observations that are really nearby our observation of interest? And we look at, was it from group 1 or group 2, those other observations? And let's say you have, 5 observations nearby, where maybe 4 of them are from group 1, and 1 of them was from group 2. And so you might be thinking, okay, how about we classify or predict the classification for this particular observation of interest then to be group 1, because its nearest neighbors are mostly from group 1. That's simply how it works. Okay? So we're going to use capital K here again. And capital K is going to be essentially how many neighbors you're going to be looking at. How many observations close to your observation of interest. So these diagrams here kind of demonstrate what I just talked about. In this particular case, so let's say we have 3 different populations or 3 different groups. We want to be able to figure out this red dot here, this observation. We want to determine should it be predicted to be group 1, 2, or 3. Now, if capital K was equal to 1, meaning I look at one nearest neighbor, and we're thinking in terms of like Euclidean distance, Typically this is actually applied in a standardized Euclidean distance setting, but let's just do regular old Euclidean distance. If I have k equal 1, then I would predict, okay, this observation should go into, let's say, grouping 1. If k was equal to 3, then I would say, okay, well, 2/3 are from group 2, 1/3 is from group 1, 0/3 is from group 3, so let's predict group 2. That's how it works. Well, what if, though, we had k equal 2? So the two closest observations are here. Now we have a tie. So what should you do for your classification or your prediction? And there's not a standard. And if we think about what software does, some software packages will do one thing, other software packages will do another. The way that R approaches it in its most frequently used function is, and I don't like this, it actually chooses a prediction at random. So maybe one time that you run this, it will predict group 1, and another time it will predict group 2. You might be thinking, well, why don't they just simply say, okay, let's look at the smallest distance. And there are some methods that will do that. And so that would be group 1 in this particular case. Another thing that sometimes other software packages will do is say, okay, if I have a tie, in terms of, if I have k equal 2, how about we just go to the next closest observation? And some software packages will do that. But R breaks the tie here in terms of this kind of a tie. There's actually going to be another tie that we'll see a little bit later, a different kind of tie. It will actually break it at random. Okay. So I've talked about this comment, this comment. The two main functions that we're going to use are knn and knn.cv. And you can imagine what that CV stands for. You probably know what it is. So it stands for cross-validation. Let me turn off some of my spell checking here. These two functions are in a package called class for classification. This package comes installed into R by default, so you don't need to install it yourself. But whenever you use these functions, you need to first say library class to tell R you want to use functions from this package. Now, the way that this cross-validation part works is essentially just the way that I just described it here, even though I wasn't calling it cross-validation, where I want to figure out, what group this red dot should be in. And so what did I do? My 3 nearest neighbors were 3 other observations. That's how knn.cv works. Very intuitive. But the way that knn works, though, is the 3 nearest neighbors would be those 3 observations. And so let's say somehow, maybe this was actually my original data set, maybe my training data set. Maybe I knew that this was from population 1. Then this particular observation would be classified into population 1, because 2/3 of the observations, including itself, are in the k equal 3 nearest neighbors. So knn assumes your observation itself is a nearest neighbor. Let's say in that particular situation, you let k equal 1. What's going to be your overall prediction rate or your classification rate, correct classification rate? If k was equal to 1. It's going to be 100% always. So you can see the bias that can happen. Essentially, it's resubstitution. But you're using just one nearest neighbor, and that one nearest neighbor has to be the actual observation itself. Okay, so let's look at a simple example so that we better understand exactly how these two functions work. So we simply have 4 observations. I put these 4 observations into a data frame called set 1. 2 observations are from population 1, and 2 observations are from population 2. Here's a plot of these observations. I purposely drew these observations or chose these observations in a way such that the distance between 1 and 2 is exactly the same as the distance between 1 and 3, and you can see similar distances throughout. Essentially, we're forming a square. Okay. I can go back to what we learned in cluster analysis to find a distance matrix or matrix of distances. Again, you would normally apply nearest neighbor classification with standardized data. I am not in this particular case, just for demonstration purposes. Now, in the data frame itself, let's make sure you see the format here. I have 2 variables, x1, x2. I also have a variable called pop for population, the group. And so then when I find these distances, notice I remove that 3rd column from the data frame so I can find the distances relative to x1 and x2. So the distance between 1 and 2 is 1. And so, in fact, you can see, indeed, on this plot, yeah, that distance is definitely 1. Okay. Let's see here. Sorry. So let's look at KNN in this setting where essentially we have capital K equal 1. So first I say library class. Then I say KNN. I need to specify a training data set. So I put set 1 there. I remove that 3rd column because that says what is the group of the observation. For the CL argument, that stands for classification. In other words, what was the original group for the data? This is then where I say, let's take that 3rd column out of set 1 and use that. Then I say, well, what, let's say, new data set do I want to test these results on? This is a little bit like a validation data set, but what I chose is, how about we just use the original data set itself? So essentially, we are fully using what would be equivalent to resubstitution. Now, the results then are put into an object called NNC1 for the lack of a better name. What's returned to us isn't the best. It simply gives the actual predicted groupings, ordered by observation number. So observation 1 is going to be predicted for group 1, observation 2 is group 1, observation 3 is group 2. I can't use the summary function with this returned object. I'm not going to get anything that's useful. Also, what we see here, we see something called ATTR prob. This uses an older version of how our objects were constructed. ATTR stands for attribute. And what this attribute corresponds to is then essentially the probability that observation 1 will be in group 1. So if I'm using one nearest neighbor, and since I'm using the nearest neighbor, I include the actual observation itself, then I have 1 over 1, or 1 is the probability. Let's look at this one here, this 2. Notice its probability is 1 as well. What the probability that's returned to us, unfortunately, is only the highest probability. then that means then for a classification for group 2, the highest probability or the probability for group 2, in other words, the observed proportion. I should say that instead. The observed proportion of my k equal 1 nearest neighbors was 1 over 1 for group 2. Now you can imagine other settings where you have maybe, let's say, more groups, a larger data set and stuff, a larger value of k. You will still only get the probability associated with the actual group that the observation is classified into. That's it. And so you won't know, well, was it close? Between, let's say, group 1 and group 2? You won't ever know that. You only will know the largest probability, or largest observed proportion. Notice here, if I were to use the names function with this, I get basically nothing in return. If I use the class function with nnc1, this tells me I have a class of factor type. R uses the general class called factor for categorical variables. And so that's all that is telling me. That essentially this 1s and these 2s are categories. But if I use the function attributes, and this is the first time we've ever done this, if I use attributes with nnc1, I get what looks to be then essentially a list in return. And so we see the 2 levels for our groupings. We see the class. We see those observed proportions as well. And so if I want to, let's say, extract out the observed proportions, then I can say attributes, parentheses, nnc1, end parentheses, $prob. That's how I can extract information. So it kind of works like a list, but it's not quite. And so when I do that then, or when I then go back to my original data set, very often you want to do something like this. You want to actually create another column corresponds to the classification. If I just simply put nnc1 there, then I'm just going to put in what those classifications are. Okay. We've already talked about these questions here. Let's now look at what happens when we change k. So let's say that k is equal to 2. We're still going to use knn in exactly the same way. But notice, and maybe I failed to mention this, there's my k argument, k equal 2 there. Yeah, before we use k equal 1, I just unfortunately skipped over that in terms of the coding. And when you say prob equal true, that's what allows you to get that, to see that part. Okay. So this is what we get now. Observation 1 is group 1, observation 2 is group 1, observation 3 is group 2, observation 4 is group 2. This is actually what was actually observed in terms of the groupings. But now I have different observed proportions here. How is R calculating that? Well, let's go back. Let's look at our plot here. Let's see. Let me just take a quick look at that. Just a second here. Okay. Yeah. I remember when I first put these notes together, I was like, oh, geez, this is frustrating trying to figure out all these small little details. Okay, so let's take a look at observation 1 here. It has a distance of 1 between observation 1 and 2. But it also has a distance of 1 between observation 1 and 3. So we have a different version of a tie here. How does R break the tie? Well, it will actually now include 2 and 3 in our calculation. So even though we say k equal 2, essentially k equal 3 is used here. And for the for population 1, we have now 2 observations out of 3 that correspond to group 1. Why do I have 2? Here's 1 and here's 1. Now for population 2, we have 1 out of 3. So whenever there's a tie in terms of the distance, it includes all ties in terms of the number of nearest neighbors. And this happens throughout now the data set. So that's why you see 0.67 there. In other words, 2/3.
Because we have the same distance, if we didn't have the same distance, we just consider 2.
Yeah. Yeah. So, want me to explain it again? Okay, so capital K is equal to 2. And the way that this is working is that the nearest neighbor overall is going to be 1. Okay? Then what's the second nearest neighbor? Well, we have a tie between observation 2 and we have observation 3. So since there's a tie in terms of that distance, then R is going to say, let's include all ties. So now, then when I look at, well, what's the observed proportion for my neighbors? I'm going to have now 3 neighbors instead of 2 neighbors. And overall, of these 3 neighbors, 2 of them are from population 1, 1 of them is from population 2. Does that help?
Yeah.
Okay.
Another question in your code. Can you fix your code?
Sure.
So what was that 1122?
This is the actual predictions. So, and this is ordered by observation number. So observation 1 is group 1 in terms of the prediction. Observation 2 is group 2. Observation 2 is group 1 as well. So those are the predictions.
And each probability is for each of them?
Yeah.
Like one by one?
Yep.
Why is the second group? I thought that it should also be 2, right? You made that one. Since the distances are the same.
Okay. So I think your question is, why is this 1 over 3? Okay, that's because this is observation 1 and 2. This is observation 3. That's why.
And I thought that one should also be like observation 3 and 4 for group 2. Since the distance is from.
Now, the distance between 1 and 4 is not 1. It's actually 1.4. And so that is a particular case where we have a little bit longer distance. So that's why observation 4 was not in that group. And so we can just do one other quick example here. You know, let's say if I'm interested in observation 3 here. Now in that particular setting, we will have this, because observation 3 is population 2. Then I have the tie between 1 and 4. And so 4 is population 2. That's why I have a 2 there. What if now k is equal to 3? Notice each time I have 2/3. If we go back to observation 1, okay, we have that as being, let's say, in its k equal 3 nearest neighbors. Then we have a tie between 2 and 3, but notice this is now k equal 3, and so we just stop. And so that's why we get exactly the same results. Let's say that k was equal to 4. What's going to be those probabilities, or those observed proportions? It's going to be 2 over 4 every single time. And in fact, here it is. Yeah, that's disappointing. Excuse me? It still gives you information about the strength of what you think for that classification. So if I have, let's say, 0.99, it's like, okay, yeah, I feel good about that. But if I only have, let's say, 2 groups and I have a 0.51, then it's like, well, that's not the best. And so again, then when you're following up, after you look at the overall correct classification rate, and you're following everything up, you might be looking, okay, where are the ones that are kind of close? And then I could go to maybe some of my plots to see if I can see which ones have probabilities that are close. And that might lead you to some conclusions about where this method is having problems. Now, if we look at this right here, this is what R says as for the predictions. It predicts 3 of them to be in group 1 and 1 of them to be in group 2. Not 2 of them in 1, 2 of them in 2. Why does it occur? What's that? Yeah, this is where the random part comes in. Is that since this probability is a tie, then it's just going to randomly choose a grouping. So because of that, then, it's always good whenever you use this function to set a seed beforehand so that you can replicate your results. Okay. Let's look at now using knn.cv. So now we get to, I think, what is more intuitive about how to actually approach this, where you don't include the observation itself in the set of nearest neighbors. So this is how knn.cv works. I specify my training data, so set 1 without that third column. Then I have the CL argument again, which stands for the classifications for those observations that are in my training data. I'm going to use k equal 1, prob equal true. And this is what I get. Observation 1 is going into group 1. Observation 2 is going to group 1. Observation 3 is going to group 2, but observation 4 is going to group 1. Well, why? Take a look at these observed proportions. They're always 0.5. And so we have this R choosing stuff at random. And so again, this is an example of you should set a seed beforehand. So why am I having 0.5 here? Well, let's go back to our plot. We'll think about observation 1 once again. So this is what I want to classify, and I look at what one observation is closest to it. Well, we have a tie, 2 and 3. And so because of that, R takes all the observations in the tie and has 1/2, we'll just do this, 1/2 and 1/2 here, and then R breaks it at random in terms of the actual final prediction.
Can you explain the seed
Sure, it's actually CL. Yeah. This stands for the classification. So, what I usually refer to as what we observe in our data set, our group or our population number. It just uses the term classification instead.
When you say k equals 1,
Yeah.
is that default? We choose the observation itself as
Not when I'm using CV. So like cross-validation, remember with cross-validation with discrim analysis, we would remove our observation from the data set and then apply the method. That's essentially what's being done here. If k was equal to 2, look what we get here. Well, we get exactly the same thing. Because we always have 2 observations based on how I constructed this data that are always equal in length from that. What if k was equal to 3? Now, essentially, for observation 1, let me do some erasing. Notice for observation 1, here are my 3 nearest neighbors, the remaining of the data set. And there's always going to be 2 observations from the other group. So, in other words, everything will always be misclassified for this particular, because of how I constructed the data set. Okay? And here you can see that. So, I think this is a nice, simple data set to have a feeling for exactly how nearest neighbor classification works. That's why I put it together like this. You can see that this capital K plays an important role. So how do you choose K? Perhaps, before you apply any kind of really formal analysis, you should go back to our graphics section. You do some graphs or plots of the data. And maybe from those plots, by chance, you might be able to get a good feel for what maybe K would be. Oftentimes you're not, but still it's worthwhile to do that beforehand. But often what you see done, and this makes sense, is that the value of K chosen is just results from trying a bunch of different values of K, finding which one does the best in terms of your overall predictions, your overall rate, or it could be just based upon, let's say, one of your groupings, or 2 of your groupings, or 3 of your groupings, or 3 of your groups. Look at the individual grouping correct classification rates. And so let's apply some of these ideas then to the place kicking data. So I have my place kick data set, my training data set, and then I have my validation data set is what we've had before. Again, the way that this is typically applied is that you're going to use standardized data. So the first thing that I do is I standardize my data. Notice the -9 there. That is my good variable, which tells me it's a success or failure. That's why I took that out. I also show here the means for each of the variables. Remember, I have a validation data set. Will the validation data set have exactly the same means for each variable? No. Okay. But eventually, though, I'm going to want to standardize my data, my validation data set, and then apply this classification method to it. So since the means aren't going to be exactly the same, that means when I standardize my validation data set, I need to take that into account. I need to actually use the mean from the training data set, also the standard deviation from the training set, when I do the standardization. So instead of using what we've always seen before, is I use the mean from the data set itself, then when I do the standardization, the standard deviation from the data set from when I do the standard deviation, I actually need to use the values from the training data. Here's an intuitive reason why to understand why. Let's say that you're a football coach, you got your Surface Pro on the sideline and you need to decide, if I do a field goal here, will it be a success or a failure? So essentially, I want to predict one future observation. But then your statistician who's right next to you on the sideline says, hey, you need to give me what the standardized value for the distance is. And the coach is going to look at you kind of weird. What would you use for the mean to standardize it? What would you use for the standard deviation? You don't have a way of doing it because you just have one observation. So what you would need to do is, for your training data set that you use, let's say before the game, use the mean from that, use the standard deviation from that, and then do that same usual calculation for the standardization. Take the distance minus the mean from the training divided by the standard deviation from the training. Okay. So what we need to do is, let's see here. There we go. So how would I find, again, all the means from the training data set? Quickest way to do that is use the call means function, which means column means. How would I find the standard deviations from the training data set? The quickest way, and I think we've kind of looked at this before, is to use the apply function, where I apply to my data in the x argument the function SD for standard deviation. How do I want to apply it? I want to apply it by column. And that's what margin equal to means. They could have made it more descriptive, but that's what it is. And so that's how I would do that. And so when I use now the scale function to find my standardized values for my validation data set, I modify the code from what I've used before. I still put in my validation data set, but now I use an argument called center, and that's where I put the means from the training data set. I also have an argument called scale, which corresponds to the standard deviations. And so that's how I can standardize my validation data. Okay, we're running out of time here. So let me briefly mention this project. So you're going to apply nearest neighbor classification to your data set that you're using for the project. And number one here is that you're going to first find an appropriate value for k, and that's essentially what we're going to do next in our notes, which basically means we're going to use a for loop to try k equal 1, k equal 2, k equal 3, and so on, and then look at the correct classification rates. Based upon that, we'll make a judgment about what value of k should I use. That will get you started with number one. Then number two is that, well, given that particular k, let's do an overall summary. And so we're going to go back to that summarize.class function that we saw in discrim analysis and construct a table that tells us which ones we got right, or how much we got right and how much we got wrong. And I'll wait on the rest of the stuff, but you're going to see some parallels to what we did with discriminant analysis. Okay, so in terms of what's next in our class, the usual office hours. On Tuesday, we will finish up nearest neighbor classification. We will also maybe start logist regression, and then looking further ahead, again, project number 3 is due on November 21st. Test number 3 is November 30th. Are there any questions? Okay, that's all for today.